Good morning to all of you. With my regards to chairpersons and the organizing committee of the 73rd Indian Pharmaceutical Congress, it's a pleasure and honor for me to be here with you this morning and to share some insights into this particular topic, which is basically an overview of descriptive and inferential statistics. As you can make out from the title of this session, that this is targeted at the students rather than seasoned researchers. Okay, so for most of us who are in the biomedical fields, whenever the question of statistics comes to our mind, we are rather afraid. Can you show the first slide? The reason is that we are not career statisticians. Mathematics is not our strong point. But whenever we encounter data, whether it is in other fields, whether it is in medicine, whether it is in public health, we require some tools, mathematical tools for analysis, and that is what is statistics. So statistics is basically a set of mathematical tools which helps us to analyze data and interpret it. Now, can data be analyzed without statistics? This question was put to Ernest Rutherford. So, if you recall, Ernest Rutherford was a physicist, and this was his reply, which is rather dismissive of statistics. He said that if your experiment needs statistics, you ought to have done a better experiment. Now, Rutherford was a physicist, and physics and chemistry are supposed to be the exact sciences. But those of us who are working in biology or the life sciences are not so lucky. So, we have to contend with biological systems which are inherently variable. You take a simple thing as blood pressure. We know that blood pressure varies from one individual to another. In the same individual, whether the person is at rest or he has exercised a little bit, the blood pressure will vary. In the same individual, even if he is at rest, if you take the blood pressure in the morning and if you take the blood pressure at night, it will vary. So there are immense variations in almost all biological variables that you can think of, and most of the time, we are not aware of the sources of these variations and neither only control or check these variations. One other thing. In biology and particularly in medicine, we are often interested in small changes or differences rather than in big effects. So, if you recall, when penicillin came into the market, it was a wonder drug. There was hardly any good antibiotics at that time, and penicillin made a dramatic impact by saving lives. So, at that time, maybe the existing antibiotics had a cure rate of 20 to 25%, and penicillin came into the market with a cure rate of 95%. So that was a revolution, a dramatic discovery. But if I give you two antibiotics today, you won't get that type of difference. Maybe one will have a cure rate of 95% and another will have a cure rate of 97% in a particular infection. And if I ask you, okay, choose the better antibiotic, you keep wondering that, okay, there is an observable difference of 2% in cure rate, but is that a meaningful difference? Is it quote unquote significant enough for us to change our practice of using one antibiotic and replace it with another antibiotic? So, making sense of small changes in the face of all these biological variations requires some tools when we want to analyze our data, and these tools come under the umbrella of this discipline that we call statistics. Therefore, today, in all branches of science, even in medicine and public health, we require applications of statistics, and we need to understand the basic principles of statistics definitely if you are doing research. Next one, please. Okay. And if you are doing clinical research dealing with human beings, the source of variation is multiplied 100-fold. So look at this statement made by a rather frustrated researcher. There could be no worse experimental animals on earth than human beings. Why? They complain, they go on vacations, they take things they are not supposed to take, they live incredibly complicated lives, and worst of all, they forget to take their medicines on time. So you build a set of variables, you think of a set of confounders in your experiments, and look, the subjects are introducing many more confounders which you never even expected. Next slide, please. Now, what is the goal of medical statistics. So in statistics, we start off with measurements or observations. So measurements or observations we express as numbers. Now, often what we do is we take a series of measurements or make a series of observations. So we have in our hands a series of numbers. So we call these numbers a data series or a data set. Okay. So when we have a series of raw numbers, how do we make sense of that? Say if I have a set of, say, weight values, the weight of 1,000 individuals in my hand, and I ask somebody, okay, what do you make of these 1,000 weight values? Are you dealing with a group of people who are thin or they are fat? So just by scanning through 1,000 numbers, it is very difficult to say this. You need to have some means of summarizing these numbers. So how do you summarize? So at the very basic level, when you summarize a series of raw numbers, you try to see whether there is some sort of midpoint or central point in that set of numbers. So in statistics, we have a basic set of measures called the measures of central tendency. And you can all name that there are three measures of central tendency: mean, median and mode. So once you have identified the central location, you try to see how the rest of the numbers, those which are not at the central location, they are dispersed about that central point. Are they widely dispersed or they are tightly dispersed? So to describe that, statisticians have devised the measures of dispersion. And you know that things like range, standard deviation, interquartile range, these are measures of deviation. So if I say of these 1,000 numbers, the mean is 65 kg and let's say the SD is plus minus 5 kg. So you now start having a mental impression, okay, I am dealing with a group of people who are neither too fat nor too thin. They are about average for Indians. So you need some measures to identify patterns in numbers. Most of the time, or many of the time, we stop here. But sometimes we go to the next step. What is the next step? We start comparing one series of numbers with another series of numbers. And comparisons we do for different reasons. Sometimes for finding out a difference, sometimes for looking at associations, sometimes for looking at agreement. And there are other reasons for comparisons. And why do we compare? We compare in order to see whether we can generate some information which can be used beyond the immediate population or the immediate sample that we have studied. In other words, we want to have some generalized information. If today, in sitting in my institution, I do a study on antibiotics and say that it has a cure rate of 95%. Now, I want to generalize this. I want to generalize this and say, okay, this particular antibiotic, wherever it is used, is going to have a cure rate of 95%, not just in my institution. So, this generalization of information is what we do by applying statistical principles. So, we use statistics to generate generalizable information, which today we are calling evidence. So, the age of medicine is moved from eminence-based medicine to evidence-based medicine, and statistics gives us the means to generate this evidence. Next slide, please. So, leaving aside administrative issues, what does a doctor do? A doctor basically has three tasks. He has to analyze some signs and symptoms, take the history, and arrive at a diagnosis. Now, many of the times when we start a treatment, we don't have a confirmed diagnosis, we only have a working diagnosis. So, on the basis of the diagnosis, we start our management. We start our treatment. So, management may be for curing some disease, management may be controlling some symptoms, management may be preventing some complications. So, we have a management plan, let's say plan A, we execute that. If plan A works, fine. If it doesn't work, we think of a plan B. Plan B works, fine. Doesn't work, we think of a plan C. provided we have a plan C. If not, we go back and try to revise the diagnosis. Now, all through this process, what is the patient or their caregivers they are interested about? They are not interested about the details of your plan A or plan B. All they are interested in is what is going to happen to them. So they'll ask the doctor, what will happen? Where will I be? 1 week from now, 1 month from now, 5 years from now. So the doctor will also have to tell the future. This is called prognostication. Now, how does a doctor tell the future? He or she is not a magician. So what the doctor does, the doctor looks at the experience of treating that illness and then looks at the specifics of that particular patient. And on the basis of that, they try to prognosticate, tell the future for the patient. So these are basically the 3 areas that a medical person goes into. Next one, please. Similarly, when we apply statistics to questions of medicine or public health, we do it in 3 domains. First, we try to use numbers to describe a situation. So this is called descriptive statistics. In the next part, we try again to use numbers to see whether we can draw some conclusions, let's say regarding the plan of treatment. So this is called inferential statistics, drawing conclusions. And finally, again on the basis of numbers, we try to predict the future. And this predicting the future is an area of little advanced statistics. We call it statistical modeling. So whenever you encounter terms like regression, distribution fitting, etc., these refer to statistical modeling. Next one. Now, before we go into elements of descriptive and inferential statistics, we need to understand 2 or 3 fundamental principles. The first one is that most of the time we cannot do studies covering entire populations. We have to depend on subsets of the population, which we call samples. Can you press the next one, please? Let's say I'm trying to answer a research question regarding that population by using a sample represented by that yellow circle. Now, someone may be trying to address the same question by drawing another sample, another circle. Now, is there a difference between the 2 circles? Obviously. There's a difference in size. There is a difference in location. So, samples can vary in their size and in their location within the population. But let's say I take a very small circle lying in one corner of the ellipse and then claim that the findings from that circle represent the whole ellipse. Will you agree? Will not agree. Why? Because we'll say that, okay, the circle is too small and the circle is lying in just one corner of the ellipse. It is not covering the whole population. And therefore, you cannot think that this circle will represent the situation for the whole population. So whenever we do studies, can you press the next one? Doesn't matter what kind of study you do. You may be doing a clinical trial. You may be doing an epidemiological work in the field. You may do a quality control study in the laboratory. Whatever you do, this question, the size of the sample and the location of the sample, in other words, the sampling strategy, are 2 very fundamental things in statistics. Unless you get these things right, the rest of your work will actually be worthless. They cannot be used meaningfully for the whole population. Next one. Now, the raw material for statistical work is data. You all know that. But all data do not carry the same type of meaning, and there is a classification or hierarchy of data. And in this slide, I'm trying to summarize that hierarchy. So at the very basic level, we'll say the data is either quantitative on your left hand side or qualitative on your right hand side. So what is the distinction? For quantitative data, we get the values through measurement. And if we have to make a measurement, we need to have an appropriate measuring device. For qualitative data, You don't need to do a measurement. You look at some characteristic or some attribute, and on the basis of that attribute, you can state the value of that variable and categorize your sample into categories. To give an example, let's say human hair. If I speak of the length of human hair, what kind of variable would it be? It would be quantitative, because you'll have to measure the length of the hair using a ruler or a tape measure or whatever it is. But if I say color of human hair, so technically it is possible to measure color. Okay, computers do it. On the computer screen, they use numbers for hue, saturation and brightness to define a color. But most of the time, we're just looking at the hair and looking at color as an attribute or feature, we can name the color. Okay, this is black, this is gray, this is white, like that. So hair color, we'll say that it is a categorical or qualitative variable. Now, if I ask you that, do you think that any of three hair colors, black, gray and white, are more important than the others? You arrange them in the order of their importance. You may think, okay, white hair is most important. I'll say black hair is least important, gray hair next, and white hair is most important. So I'll put it in that order. But somebody will say, no, the hair colors order doesn't matter to me. All colors are equally important. If you can identify order in a categorical variable, then you will call that type of categorical variable as an ordinal variable, ordered categorical variable. If not, you'll call it simply as a nominal variable, because the value has come from naming the attribute. So some things have a natural order. If I say what is the intensity of pain after having a tooth extracted, we'll say that, okay, pain can be absent, mild, moderate, severe or even intolerable. So this variable with its different categories, mild, moderate, severe, has a natural order. It is definitely an ordinal variable. Now coming to this side, numerical variables. Some variables can take any values within a range, even fractions and decimals. We'll call them as continuous variables. But some, we will usually not use fractions or decimals. We'll usually treat them as integers. So these are called discrete variables. So these distinctions are important when you are trying to use different statistical tests and trying to get some inferences out of these tests. Now, some more terms are given out here. Binary versus non-binary. So any variable, qualitative or quantitative, it takes only one of two possible values. Let's say present, absent, reactive, non-reactive, true, false type variables. We'll call them binary. If not, they'll be non-binary. In modeling situations, we use the terms dichotomous or polychotomous, but not in all situations. Independent versus dependent. Let's say your age and height. Does your height depend on your age, or does your age depend on your height? Obviously, you'll say that a person grows taller with as the person ages. So, height depends on age, at least till a particular age. So, when we are exploring the relationship between variables, we'll say some variables, their values may depend on the values of other variables. So, some variables are dependent and some variables are independent. And when we are trying to understand the relationship between a number of variables, more than two, we'll say, okay, some variables are outcome variables whose values will depend upon predictors or explanatory variables. Let me give an example. I'll say, okay, I'm a male person, my age, wrong side of 50. Do I smoke? No. Do I exercise? No. Do I have high blood cholesterol? Yes. Do I have high blood sugar? No. So given all these variables, what is the chance that I'm going to die of a heart attack in the next 5 years? So this variable, probability of dying on a heart attack, is the outcome variable, and its value depends upon so many explanatory variables. But in the same situation, there will be some variables. Let's say genetics of my heart's channels. You know, the heart is a very complex thing. Its action involves sodium channels, potassium channels, calcium channels, so many channels. And some of these channels can have genetic defects, and suddenly they can cause sudden cardiac death. So when I am studying this phenomenon, I am not in a position to study the genotypes of the sodium channels, but I know that they will be influencing the results. They are there, they are existing. But I am not able to study them, or I am not able to control for them. So in this study situation, the sodium channel genes will become confounder variables. Last one I am coming to shortly. Next one, please. So with these two fundamental things, idea of the types of variables and the idea that we often have to depend upon sampling to arrive at results, we'll look at the purpose of descriptive statistics. Now the whole purpose of descriptive statistics is to describe patterns in numbers. Now you're seeing, you can say, a pattern on the screen. Can you describe this pattern? If I ask somebody, you may start trying, okay, there's a ball, something like the sun in the center, rays radiating from that sun, they are wavy to begin with, then they are straightening out. What's the color? Yellowish on one side, orangish on another. So you are able to give a rough description in words. But if I tell you, now describe it in sufficient detail, so a person who is an artist but who is not in this hall, is sitting in that hall, will hear your description and draw that pattern on his screen, on his canvas. Can you do that? That would be really challenging. But you may or may not be surprised if I told you that this particular pattern which you are looking at right now is the visualization of a mathematical equation, a little bit complex equation. They call it quadratic equations. And you give that equation and the software to convert it to a picture to any computer, and that computer will reproduce the exact pattern on its screen. No difference from what you are seeing out here. How is the computer doing that? On the basis of numbers. So that is the whole purpose of descriptive statistics, to describe situations in numbers. Now I have given just two examples of descriptive situations. Okay. First one is like a typical clinical trial. You are using two antiplatelet drugs in, let's say, ischemic heart disease patients, and after giving a treatment, let's say for 5 years, you are trying to find out how many in the aspirin arm have died of heart attacks, how many in the clopidogrel arm have died of heart attacks. What is the description required? You just say, okay, in the aspirin arm, X percentage have died, in the clopidogrel arm, Y percentage have died. Now if there is a difference between X and Y, you might be interested in seeing whether the difference is important. But description wise, it doesn't require much, just 2 percentage figures. But look at the next statement, just 4 words. Mortality pattern in India. Can you describe it as a single percentage? No. Ultimately, mortality in Indians would be 100%. All Indians are going to die, unless medical science is going to come up with a miracle. So how do you describe a mortality pattern in a large country like India? You will have to start with age-specific mortality, gender-specific mortality, cause-specific mortality, area-specific mortality, and you ask people in public health, they'll say, okay, if you're speaking of age-specific mortality, let us do an age standardization. And there are 2 methods. We'll use a direct age standardization, or we'll do an indirect age standardization. Then they'll say, let's also calculate an SMR. You say, what is an SMR? Now, SMR is standardized mortality ratio. Why do you need to calculate an SMR? No, suppose we want to compare India's mortality experience with, let's say, Japan's mortality experience, and the age structure of the Indian population is quite different from that of Japan. So you need a comparable index, and that is SMR. So what I'm trying to say that in descriptive statistics, there are always some basic measures. Can you come to the next slide? there are some basic measures. And what are these basic measures? Your measures of central tendency and your measures of dispersion, which we just now spoke about. And you also have your counts and percentages for categorical variables. But beyond that, in every field of study, some additional descriptive measures have evolved. Like I gave an example of the field of mortality studies. So if you're working in a particular field, if you're working in cardiovascular sciences, if you're working in neurological sciences, you're working in endocrine and metabolic sciences, different descriptive measures of statistics have evolved over time. And you need to be familiar with these special measures in addition to the basic measures, so that your research would be comparable with the studies done by others and people will take it seriously. And ultimately, you use these descriptive measures to describe patterns in numbers. Now, statisticians don't use the word pattern. Their favorite term is distribution. So they'll say, let's speak of a data's distribution. Now, there are umpteen kinds of distribution, as you can see on this list. But if you need to be familiar with one distribution, that should be the most common distribution that we encounter in nature, and that is listed at the top as the normal distribution. And I think most people out here would have some mental image of the normal distribution. Next one, please. So, if you look at that currency note, which is the German Deutsche 10 Mark note, you'll find the picture of that normal distribution curve, and all of you are familiar with it. The bell-shaped curve, named after Carl Friedrich Gauss, the famous German mathematician and physicist. So this is the basic distribution curve, but depending upon the area of descriptive statistics where you are going into, you also need to look at other distributions. Next one, please. You can skip to the next one. So just to give you an idea of how prevalent this is, if you do the mathematics of landforms, you will encounter distributions like this is a normal distribution. Next one. Again a normal distribution, Matterhorn in the Swiss Alps, but with a sharper peak. We say it differs in kurtosis. Next one. This is not a normal distribution, but a distribution with a long tail to the right. The sand dune in the Arabia. This is a, what we say, a positively skewed distribution. Next one. You look at the iceberg in the background, not the one in the foreground. Again, you have a long tail, this time to your left. This is a negatively skewed distribution. So whenever you go on a vacation, think about, look around you, there's mathematics in nature. Next one. Okay, the last thing about descriptive statistics which I want to tell you is this concept of the confidence interval. Now, that is not very familiar to most of us. A lot of things are written out here, but let me tell you in a nutshell that if you are doing a study from a sample, say you are calculating the mean of a sample, you are not studying the whole population, then can you find out the mean of the whole population? The answer would be no. Why not? Because you are not studying the whole population. True. But can you have some idea of the mean of the whole population? Yes. If you do your one sample study and your sample is adequately representative of the population, then you can calculate a sample mean, and at the same time you can calculate a range of values, not a single value, but a range of values which will contain the population mean as well as your sample mean with a certain level of confidence. So in the life sciences, we use the 95% confidence level, and that is the concept of the confidence interval. So you can state your sample mean with a 95% confidence mean. That will give you an idea of the population figure, and it also has several other useful applications. For instance, we can use it as a basis for simple inference. Can you skip to this? You can skip this also. Go on. Yeah. So we spoke about the confidence interval. Now we'll change over to inferential statistics. Go on. Okay. Now inferential statistics basically deals with a number of statistical tests to draw some conclusions. Okay. And those of us who are new to statistics, can you press it again? Those of us who are new to statistics feel frustrated by so many tests. when to use them, where to apply them, what are the pros and cons, etc., etc., etc. But we can console ourselves by telling that none of these statistical tests were evolved as mathematical curiosities. All these statistical tests were evolved to solve some real world problems. But as it happens in science, that once you have somebody giving a method, other people refine that method. So somebody gives an original test, other people define some better tests. So a number of tests accumulate over time. But there are also roadmaps which help us to select and correctly apply those tests. And I'm going to speak about few roadmaps in the next 2 or 3 minutes. Now, the most difficult thing about inferential statistics is that it starts with something called a null hypothesis. So why do we need a null hypothesis? Now look at this side. We are seeing 3 pictures. Now these 3 pictures are representing 3 different phenotypes of a particular organism, the fruit fly. You know, it's a favorite experimental model in genetics. And if I ask you to list out the differences between these 3 pictures, there are a lot of differences. There are 3 different phenotypes of 3 different genotypes. So these are different. Next one, please. But if I ask you, are these different? If you look closely, you can identify 1 or 2 differences. Let's say you can identify differences in eye color, the wingspan, so on. But are these few differences sufficient to conclude that these 2 pictures are representing 2 different genotypes? Or are they representing just chance phenotypic variations, environmentally induced variations of the same genotype? Just by looking at these 2 pictures, you cannot answer this question because the differences are small, the differences are narrow. To do that, we need to resort to the principles of hypothesis testing, and hypothesis testing begins with a concept called the null hypothesis. So this is the conservative position when we are comparing 2 treatments or 2 pathways or 2 drugs, let's say A and B. We can have many hypotheses that A is better than B or B is better than A, but a statistician will start with the first one listed, 80, the null hypothesis, whose assumption is that there is no difference between A and B. Then they'll ask for your data, and on the basis of that data, they will try to arrive at a conclusion. What conclusion? Whether the null hypothesis can be rejected or it cannot be rejected. Next one. And in the process of arriving at this conclusion, 2 errors can be made, and I'm sure you must have heard of these terms, although whether you understood them or not, that's a different issue. So 2 errors which can be made are type 1 and type 2 errors. The error made in incorrectly rejecting the null hypothesis is type 1 error, or what we say is alpha error, and the error made in incorrectly accepting the null hypothesis, a false negative error, is called a type 2 error. So these type 1 and type 2 errors are very important determinants of the sample size for a study. So if you want to do inferential statistics, you have to start by understanding the null hypothesis and the concept of type 1 and type 2 errors. And then inferential statistics also gives you its result in most cases as a p-value. So as a means of understanding the p-value, simply we can think of it as the maximum probability of getting the observed outcome by chance. Okay. So p is a probability value, and the convention has been said that if the probability of getting a chanced difference is less than 5%, if p is less than 0.05, we accept the result as a true difference. We accept it as a statistically significant result. But if p is 0.05 or more than 0.05, we do not accept the result as statistically significant. And basically, you can just keep pressing so that all of them are highlighted. You can press all the way down. Right. So basically what we do is, today if we have to do inferential statistics, we put our brains behind the first 2 steps. We decide on the research design and the sample size to be used, and then select the statistical test. Once you have selected it, and if you are using a computer, as most people would, then the rest of the things will come automatically. The computer itself nowadays will guide you which test to, how to do individual tests. So all you have to do is to select the test, and for that, you can skip this slide and go to the next slide. Yes. We have an algorithmic approach for selecting tests. Now, we can't speak about the full details of that algorithmic approach, but that is readily available in many statistical books, including the books where Dr. Jagdish told it about. As a representative, I'll just show you how we select the different inferential statistics tests. You can press one more. So, if our idea is we try to find out the difference between two variables, then we select a group of statistical tests in this manner. We first see whether we are dealing with numerical data or categorical data. If it's numerical data, we look at, are we looking for a difference between two groups or more than two groups? If you are looking for two groups, and if my data is parametric, parametric means normally distributed, then we select a test which is called the student's unpaired t-test, and if my data is skewed, there is a non-parametric counterpart called the Mann-Whitney u-test. And if the number of groups are more than two, the corresponding tests are called one-way ANOVA, or as you can see, Kruskal-Wallis ANOVA. On that side, for categorical variable, if you are looking for a difference between two unpaired groups, we use a test called the Pearson's chi-square test or the Fisher's exact test. If for more than two groups, Fisher's is limited to a two-group situation, but chi-square does not have that limitation. We can use the Pearson's chi-square test for the next one also. Next. So we'll skip this. We'll all skip this thing. In the interest of time, I'm skipping in the details. So you see the next algorithm. What is our research question? Similar research question, but here there is an adjective. The two groups or the data sets that I'm interested in, they are paired. They are before-after data sets, or they are related in some way to one another. And once we have identified the question, the algorithm is similar. So just you can show them the slides, and then we can go to the, we can skip 3 slides. So do I have 2 minutes? 2 minutes. So we'll skip a few slides. These are repetitive. Next one. Okay. So if we had time, if you had gone through this test, you see that counting the number of this test, you would have come to a number of around 30 or 32 tests. So somebody did a count of the number of inferential statistics tests going about in biomedical literature, and they came up with a count of 100 tests. So if you're a new researcher, if you're a student trying to do your first project or trying to do your thesis, you tend to become bewildered by this sheer variety of tests. But you actually don't need to know about these 100 tests. The same authors did some more calculation, and they showed us that if you are familiar with about 24 tests, then you can comfortably do most of the inferential statistics that you are ever going to need in your statistical lives. And if you are familiar with, say, 36 tests, you can consider yourself masters of inferential statistics. So descriptive and inferential statistics, once you have mastered those two, then you can go on to statistical modeling. And what is statistical modeling? Is basically to find out predictive mathematical relationship so as to predict some variables from other. So how do the weathermen forecast whether there's going to be rain in Hyderabad today? They look at mathematical models incorporating many variables: average temperature, wind speed, humidity, so on and so forth. The same way in statistics, we can model some outcome variables on the basis of known values of predictor variables. And the simplest modeling situation in statistics is called simple linear regression, where two variables are connected by a straight line relationship. Once we have mastered that, we can go on to multiple linear regression. Once we have mastered that, we can go on to logistic regression, and so on the path of learning goes. Next slide, please. So, while concluding, I like to conclude with one quote and one analogy. Statistics is all about common sense and good design, but remember, research has a flow. Data analysis and interpretation comes once you have collected data. But in order to collect data, you need an appropriate research design, and that research design would be tailored on the basis of a well-framed research question. You cannot bypass one step for another. It all has to come in sequence. A well-designed study, poorly analyzed, can be rescued by reanalysis, but a poorly designed study is beyond the redemption of the most sophisticated computers and statisticians that you can have. So this is a quote by two of the most famous biomedical statisticians of the living statistician, Campbell and Machine. Next one. Why statistics is difficult? Most of us, many reasons. Next one. I won't deny that is difficult. If you are speaking about medical statistics, this is only one corner of the statistical universe. But the most difficult step is the first step, to motivate yourself. Next one. And this is how we go about learning statistics, motivating yourself, acquiring literacy about statistical principle, going through journals, but most important of all, actually going down in the field to try and crunch some numbers, gather some numbers and try to interpret them with the help of descriptive and inferential statistical principles. So I'll conclude with this analogy. We say that medical statistics is like a lamppost. A lamppost has some purpose in life. It is not to support this person. What is the purpose of a lamppost? Anyone? Yeah, little loudly, I couldn't hear. Lamppost doesn't throw light. If you put a lamppost, it will not throw light. Lamppost carries a lamp. The lamp throws light. So your statistics are like a lamppost. So where is your lamp? Your lamp is here. Okay. So statistics is a tools to understand and interpret data. But in order to apply the tools, you still need your lamp. So unfortunately, like in all other fields of human activity, numbers are there, even in medicine and public health. And if you understand the principles of statistics, you'll see that numbers often tell very interesting stories. So Chairperson, sir, I'm concluding here. Thank you so much for giving me the extra time.